Okay, there's one final equation we're going to look at that does not specifically come from Maxwell relations. So we just derived an expression for G. How do we find G at constant temperature? And so that was related to the pressure. But we often are interested in changes in temperature, of course. We don't do everything isothermally. So how does the Gibbs energy change with temperature? And so we're going to go through the derivation of the Gibbs-Helmholtz equation, which answers that question. So we start with the definition of G as H minus Ts. All right, so that's just one of our ways that we can write out the Gibbs energy. And let's go ahead and divide by temperature. All right. So we get this relationship here. Now we're going to take the partial derivative with respect to temperature, keeping pressure constant. So we're going to get something a little bit wonky here on the left-hand side. We'll get dg over t dt at constant p. Then we'll take h. So we're taking a derivative with respect to temperature. There's a temperature there, so we'll get negative h over t squared. So just taking that derivative directly. And then for with an additional term, right, so it's h times 1 over t, we'll have an additional term that's plus 1 over t times dh dt at constant p, right, so we're doing the product rule here. And then we have minus ds dt at constant p. All right, so we'd like to simplify this. So we have here on the left-hand side, we have a Gibbs free energy changing with respect to temperature, but we have sort of a mess over here. We'd like to clean this up. Okay, but dh dt at constant p, this is the constant pressure heat capacity by definition. And we've previously showed that ds dt at constant p, when we were talking about the third law of thermodynamics, we derived that this is equal to Cp over T, and that's why we could integrate this and find absolute entropies. So we have here Cp over T minus Cp over T, and these two terms cancel out. And so the Gibbs-Helmholtz equation is what's left, that the change in G over T dt at constant p is equal to minus h over t squared. Or we can go ahead and write this out as delta g's and delta h's, right? Changes in Gibbs free energy and changes in enthalpy, but it's basically the same equation. d delta g over t dt at constant p is equal to minus delta h over t squared. So the change in Gibbs energy is related to the enthalpy change for our system. So if we know the change in enthalpy and how that changes over temperature, we can derive the change in the Gibbs free energy as we change the temperature for a process. So that concludes chapter 22, our chapter on the Gibbs energy, Helmholtz energy, and Maxwell relations. And so we'll see you next time for the continuation of our adventures in thermodynamics.